My name is Immanuel Bloch. I'm professor of physics at LMU Munich and one of the scientific directors of the Max Planck Institute of Quantum Optics, and I'm working in the field of quantum simulation. In quantum simulation, we really try to build many-body quantum systems that are relevant for materials, for the universe, for phenomena that we have when many particles come together. So we try to build a model system that exactly behaves like we want, and then we can study individually what the atoms are doing in this system, how each of the quantum particles interact. In quantum computing, we are trying to do something similar, but we're trying to do a specific calculation to calculate one of the properties of the system. So quantum computing can be more universal, but it's very hard and we're not there yet. Quantum simulation is more robust and makes a little bit better use of the quantum hardware, but is not universal, can only study certain kinds of problems. So in optical lattices, what we do, we take multiple laser beams and we shine them on top of each other. And because they are lasers, they are waves, you not just got twice as much laser light where they overlap, but you actually get an interference pattern. You get patterns of bright and dark spots where there's a lot of light, where there's no light. So you get alternating patches, microscopic patches of light patterns, a light crystal. And for the atoms, this light crystal is like an egg carton. So you think, you all know egg cartons where you place eggs to travel them home. So the atoms really experience this optical crystal like an egg carton in which they move and which they can behave like now atoms in a crystal now formed out of light. So right now we're working with up to 5,000 particles. These are the largest number of atoms we've had to do quantum simulations, so these are pretty large systems already. Some of the problems we're interested in are related to material science, condensed matter physics, for example, superconductivity. We want to understand how can we have materials in the real world that do not have resistance, do not lose energy when we send current from places A to B, which is a big problem today. And we would like to understand how these superconductors where current can be conducted without friction works. So this is one of the main application areas that we like to look at. Yeah, so I think one wonderful thing was that we really are able to see individual atoms in these quantum simulations, so we can really look how one atoms interact with the other atoms, atom by atom study how they are behaving together, and this was really a breakthrough. And I think now by extending our control over these systems, we're going to have many more possibilities in studying different kind of materials, magnets, superconductors, but also study behavior that is relevant to understanding our entire universe. How does our entire universe behave? And so those are going to be exciting questions to address in the future. Yeah, so what we really did there was to be able to do ultracold chemistry at the maximum possible level of control that quantum mechanics allows us. So really to take two atoms and bind them together, bring the atoms to the ground, these atoms make a molecule out of them, bring them to the ground state, and making more and more complex molecules. So out of this molecule out of 2 atoms, we made molecules out of 4 atoms. So we'd like to see how far we can push this. Can this be a controlled way of making more complex molecules in a highly controlled way at the quantum limit? So that's one direction we're interested in. And yes, of course, we're continuing with the team. We're looking forward to continued collaboration. Oh, I think I got an email telling me, so there was no real person phoning me or something. It was an email that then got me by surprise and informed me about the Misius Prize. And of course, we're very happy also to share that with Tillman and Markus together. This distinguished prize, and also seeing all the previous prize winners was a great honor.
Okay, and that's all for today's interview. Thanks for your
Thank you.